Welcome back to PV Online. Today we're going to take a look at the index of refraction. Remember that refraction is the phenomenon that occurs when light goes from one medium to another, when it hits that boundary, how the light behaves. Now this index of refraction just basically tells you how dense the medium is. The bigger the n value, the bigger the index of refraction, the more dense the medium it is. So now if we take a look at this, we've got a table over here, and you've got a table, these are constants, which means that for our purposes, water is going to always simply be 1.33. The index of refraction for air is going to be 1. Now you'll see that it's a little bit more than a vacuum, but that number is so small that we're going to kind of neglect it. The index of refraction in any medium is simply a ratio of the speed of light in air divided by the speed of light in the medium. You'll notice that I'm not putting a v for the speed of light in air, and that's because it's a constant. It's a value that's not going to change, and it has a value of 3 times 10 to the 8th. And you've probably heard of that when you've heard the equation E equals mc squared. C is the speed of light in air. So let's take a look at this. It says find the speed of light in the ethyl alcohol. Now in this case, the ethyl alcohol is going to be the medium. So we need to look at our table and we can see that the index of refraction is simply 1.36. It has no units because it's just simply a ratio. So if I were to do this, I would say my index of refraction of ethyl alcohol, I'm just going to leave it like that, equals the speed of light divided by this speed in the ethyl alcohol. All right, the index of refraction is 1.36. The speed of light in air, which is always going to have this value of 3 times 10 to the 8th, divided by the speed in the ethyl alcohol. All right, let's solve for the speed in the ethyl alcohol, and we do that by simply taking 3 times 10 to the 8th divided by 1.36. And that gives me 2.205, so I'm going to round it to 3 significant figures, 2.21 times 10 to the 8th meters per second. Now just a word of caution. If you ever get a speed greater than 3 times 10 to the 8th, you have a math error. 3 times 10 to the 8th is the largest value that we can have. All right, so now let's take a look at this. Now remember, all the index of refraction is it tells you how dense the medium it is. Now the index of refraction of air is 1. All right, let's say that we have this incident ray, and this incident ray is on this air glass boundary. Now what will that ray do when it enters the glass? Will it bend towards or away from the normal? Since glass is more dense than air, it's going to slow down, and as it slows down, it's going to bend towards the normal. All right, now as soon as we get there, the next thing we need to do is we need to draw another normal. So I'm going to draw the normal just like this. Now look at what happens here. I've got my initial angle of incidence. It goes into the glass, it slows down. That means my angle of refraction is going to be smaller. Now, for those of you who remember anything with geometry, these two are parallel lines. And since they're parallel lines, that means that these two interior angles are going to be the same. So this is going to be my new angle of incidence. And now look at what's going to happen when it goes into water. Now, glass has an index of refraction of 1.52. Water has an index of refraction of 1.33. That means it's less dense in the water. Since it's less dense in the water, what is it going to do? And it's going to speed up and it's going to bend away from the normal. So I draw my new ray. The next thing I want to do is I want to draw a new normal. And remember, the normal is always going to be when it encounters the next boundary. Now look at what I've done. I very carefully have drawn straight lines as long as it's in the same medium. These light rays are never going to start curving around. They're always going to go in a straight line as long as you're in the same medium. So now this is going to be my new angle of refraction. So we're getting too many theta i's and r's, so I'm going to call that theta 3. You can see that this is a little bit bigger than the one up here. Again, these are two parallel rays, so these two are going to have the same angle. All right, now, what's going to happen when you go from water back into glass? Is it going to speed up or slow down? Since this is more dense, it's going to slow down, meaning that it's going to bend towards the normal. So my final ray should be back towards the normal again. All right, let's do some math associated with this. And it says, find the speed of light while it's in glass with an index of refraction of 1.52. All right, so let's do A. And I know it's the index of refraction of the glass is going to equal the speed of light divided by the velocity in glass. The index of refraction of the glass was 1.52. The speed of light in air is 3 times 10 to the 8th. And I'm trying to find the velocity of the glass. The velocity in the glass is going to be smaller because it's more dense than air. And I get a value of 1.97 times 10 to the 8th meters per second. So it slowed down when it entered the glass. Now let's take a look at the next one, and it says if the light of wavelength 450 nanometers shines on the air glass surface, find the wavelength of the light in the glass. Okay, so for part B, we know that the index of refraction in glass is going to equal C, which happens to be the wavelength in air, times the frequency in air, divided by the wavelength in glass, times the frequency in glass. Now, an interesting phenomenon occurs, and that's when, as the waves encounter that boundary, the frequency with which those waves hit, that doesn't change. So whatever the frequency originally was, the frequency in the air and the frequency in the glass will stay constant. So the frequency doesn't change. All right, that's important. The frequency doesn't change, meaning I can cancel these out. Now, nanometers is the prefix 10 to the minus 9th. It's a very common prefix when we're dealing with wavelengths. And so what you can do is let's just find the wavelength of light and glass, but keep it in nanometers. So the index of refraction was still 1.52. My wavelength while it was in air was 450 nanometers. And my wavelength in the glass is going to be what we solve for, so all we have to do is take the 450 divided by 1.52, and that gives me 296 nanometers. Okay, so the wavelength got shorter when it entered the glass. Now, last but not least, let's find the frequency of the light in glass. Now, I could use, it really doesn't matter, I could use that C equals the wavelength times the frequency while it's in air, or I could use V in glass equals the wavelength in glass times the frequency in glass. It doesn't matter as long as I stay consistent. So if I use the speed of light as 3 times 10 to the 8th, then it's going to be critical that I use the wavelength in air. And the wavelength in air was 450 nanometers, so I'm going to make that times 10 to the minus 9th times my frequency. I solve for frequency and I get 6.67 times 10 to the 14th hertz. So that's how many waves will pass each second. Let's do the same thing, only this time let's use our values for the glass. So my speed of light while it was in glass was 1.97 times 10 to the 8th. My wavelength when it's in glass was the 296 nanometers, so I've got to remember to convert that to meters, times the frequency. And if all is right, they should come up with the same answer. And I get 6.66 times 10 to the 14th hertz. The big idea is simply that the index of refraction just simply tells you how optically dense the medium it is. The bigger the n value, the more the light's going to slow down. As the light slows down, the wavelength is going to change, but the frequency won't. All right, we'll see you next time.